What's up, guys? We're going to talk about light. So light and the nature of light, most of you maybe have heard this before, but light has both wave-like and particle-like properties. It's called wave-particle duality. When you look at a rainbow, you see light behaving as a wave. It splits apart. When you use a digital camera, the incoming light acts as particles that hit the camera's detector. So we've got kind of a connection to both of these ways. Or ways of behaving. Light is electromagnetic radiation, any kind of light. So UV light, ultraviolet, or infrared light, or anything like that. When we use the word light, we're referring to the visible spectrum of light, the part that's visible to humans. There are many types of different electromagnetic radiation, like X-rays and radio waves. And some people might feel uncomfortable with that word of radiation. I know there's been a lot of that with the 5G stuff that's come out, and different smart meters and different stuff like that. There's been lots of conspiracy theories, and people are very afraid of the word radiation. All right, it's something that they associate with something dangerous, like high energy particles. High energy particles emitted from radioactive atoms, we call that radiation as well. It can be harmful to living creatures. Radiation just refers to anything that radiates from a source, just like light. So it's nothing to be afraid of, and we're going to dig into it here. It has a wavelength and a frequency. So there are some things we can know about the wave part of light. Electromagnetic radiation can act as a wave, and waves carry energy, and energy is what we're really concerned about with light and measuring with astronomy. So if you look at this figure here, the distance between the two peaks that you see here is what we call a wavelength. And then the number of waves that pass by a stationary point by this dude counting in 1 second is what we call the frequency. And those two are tied together. As the frequency goes up, the wavelength gets shorter. All electromagnetic radiation have a few things in common. Electromagnetic or EM radiation travels through space at the speed of light, what we call speed of light. And this is for all electromagnetic radiation. So gamma rays and X-rays and microwaves and all that kind of stuff, all those waves and rays and that kind of stuff all travel at the speed of light. 3 times 10 to the 8th meters per second. Wavelength is represented by this Greek letter lambda, and frequency is represented by the Greek letter nu. All right, and then the relationship between wavelength, frequency, and the speed of light, those all three are related, and they're related by each of these equations here. And they're just shown in two different ways, two different orientations, with one solved for wavelength, the other solved for frequency. All right, they are an inverse relationship, frequency and wavelength. So like I said before, the higher the frequency, the shorter the wavelength. Taking that wavelength and frequency piece for an example, let's just say that there's a radio station, 89.5 on the dial. That means, if you didn't know this, but those are directly related to the frequency of waves that are broadcasting that information. So when you tune your dial in your car or something to 89.5 or whatever your favorite radio station is, that's 89.5 megahertz, or in other words 89.5 times 10 to the 6th, that's for mega, cycles per second. All right, and they want you to find out what's the length of those radio waves, and you're going to be maybe a little surprised by this, but radio waves are actually pretty big. All right, radio waves, the wavelength, so from peak to the next peak, and when you do this calculation, you get 3.35 meters. That's I can't stretch that far. All right, to give you a sense of what that is, that's like almost 10 feet. All right, or close to 10 feet. So that's pretty big. This is why radio stations, you see the huge towers. Radio stations have very large towers, not to get up above stuff. That's one reason. But the bigger reason is they have to be pretty wide, because to produce waves like this, they have to be pretty big. To produce a wave, you've got to have something that's going to push the medium to that level. All right. Are radio waves sound waves? So you get them from the radio, but are they sound? Sound is another example of a wave, for sure. Sound requires a medium. In other words, sound requires something to be there, like air or water or anything like that, to travel through. It cannot just go when there's nothing there. It has to have water, it has to have air. It's a different type of wave. All right, it is a wave that sound pushes air, all right, or pushes the medium. All right, and it creates these areas where there's the air molecules get really close together and then they get further apart, and that's how you get your wave with sound. And that's why you need air to be able to have that propagate. Light is made up of electric and magnetic fields that oscillate, that bounce back and forth. All right, they change. Okay, the magnetic field and the electric field, and they don't need atoms or molecules to do that. They don't need air, they don't need water to travel through. There's no air up on the moon, there is no sound. If you're in space, there's no sound. No one will hear you scream. No one will hear you talking. No one will hear anything. Out there in space, if you were to, obviously in the spacesuit with a microphone, there's air in the spacesuit, so the astronaut can talk. But out there in the ether, in the emptiness of space, there's not enough stuff to allow sound waves to propagate. Light does not require that medium to propagate. Radio waves are a type of electromagnetic radiation, therefore, and they're not sound waves, so they can travel through empty space. Radio waves, radio communications, this is how we communicate. This is why they have the little microphone, picks up their voice, and transfers it to the rest of the astronauts or back to the shuttle or the spaceship or the space station. The amount of energy that is part of a light as a particle, the amount of energy that a particle carries is related to what's called a photon. A photon is a packet, like a packet of waves, and this packet of waves travels with a certain amount of energy. All right, energy. This is how we get energy from the sun to have the earth be warm and have everything that we have here to kind of sustain life. So energy, capital E here, of a photon is inversely proportional to the wavelength. That's what you see here, inversely. That means the bottom. This is the proportional to sign. It means there's going to be an equation that probably comes up with something like this. It's just we want to focus on what the real relationship is. That's the energy proportional to wavelength. So that means that the wavelength gets big wavelength. All right, big wavelength. We have a very large wave. We have one over that. That's going to be a very small amount of energy. So big waves are less energy. Small waves are a lot of energy. So things like X-rays, very small wave. All right, whereas things like microwaves, much larger wave. All right. It's the photon energy. The energy is directly proportional to the frequency. So high frequency, high energy. Photons with a high frequency have high energy, and we'll see what that lays out on the spectrum here in a second. So electromagnetic spectrum, this is the whole thing. You've got your gamma rays that create superheroes down here. You've got X-rays that allow us to see through things or into your body and see your bones and stuff. We got UV, which is harmful radiation that comes mostly from the sun that can change the molecular structure of certain atoms that absorb that energy. And then we have infrared in this big area here. We got microwaves in a little bitty band right in the middle there. Then we got all your radio waves. Radio waves for TV, UHF and VHF. You got your FM radio, you got your AM radio, and you got this whole entire piece over here for radio communications. A lot of that stuff is protected by the FCC governing that. Visible light is this little tiny piece right here in not really even in the middle, but right there near the middle. And it has short wavelengths, purple and blues, that are high energy, and then you've got long wavelengths like the reds and the oranges that are going to be long wavelengths or less energy. So less energy needed up here or carried by the waves and packets, and more energy carried down here. Common lengths of measurement that we use in astronomy. One thing is called the nanometer. Nanometer is 10 to the negative 9th meters. That means 9 zeros and then the number in front of it. So 0.9 zeros and then that. And then an angstrom, which is minus 10. Just one more thing, right? Average wavelength of visible light is about 0.0005 millimeters. So we're on the scale of, fractions of a millimeter for visible light. Scientists generally use nanometers to describe light in wavelengths, the wavelength of light. A nanometer is a billionth of a meter. Another unit we use is the angstrom. We already talked about that. Visible light ranges from anywhere from 400 to 700 nanometers. So 400 nanometers for the short waves, that's going to be your almost ultraviolet. Anywhere just past or under 400 is going to be UV, so your purples will be 400. And then 700 is going to be red. So the color actually comes from that wavelength of light. So that's pretty cool. We'll talk about the infrared and the edges of the spectrum in our next video. Thanks.